So in the previous video, pretty much this relationship was derived using the Leibniz rule and Gauss, a bit of assistance from the Gauss. So basically the time derivative of a scalar function that depends on time and a time-dependent volume can be basically expanded into this form, where the derivative with respect to time is moved inside, which basically results in a partial derivative with respect to time of the scalar field, and then a number of terms that depend on time through the actual velocity of the vector field. It's as well as the actual velocities in the vector field that are actually causing the volume to move into form as it moves through the vector field. So the next step in this process is to basically use this equation on the first part of the Euler equation, which is basically, this is basically the mass times acceleration part. So this needs to be expanded using that. So the basic idea here is that rho as a function of space and time times the component of velocity as a function of space and time is basically just a scalar field. So this is basically just a scalar field that is a function of space and time. So the basic concept is simply to replace the scalar field with the function, these two functions. So doing that leads to the following. Basically has this thing and this thing, this dt term of the blob that depends on time, this will simply be converted using Leibniz rule. So this turns into an integral over the same blob, which is the volume that depends on time. And then it has a partial derivative dependence on time times rho and this is actually the partial of this whole thing. Basically do this again, and this is just essentially replacing symbols. Space and time. Gradient u vector. I'm going to drop the x and t because I'm running out of space. And that's actually the divergence, not the gradient. And then this thing times rho. Dot product by u vector. Actually, I'm gonna have to cheat and move the blackboard. So I'm totally running out of space. Product with u vector. And then trying to change the volume. So this should just be the rho ux being substituted in wherever there was a Greek symbol there. And double check checking that I actually got this right. Okay. So right now that's still pretty messy, and it really doesn't need to be written out in that form because there's actually a simplification, and the simplification comes from the fact that in this case, that this particular series of videos will only deal with incompressible fluid. So incompressible fluid implies a couple of things. One of it, which implies that rho that originally depended on space and time, no longer that depends on that, so it goes to just rho a constant. And the other thing that it implies is that the gradient of u, the velocity field, in space and time equals 0 everywhere. So this actually comes basically from Gauss's law again. So Gauss basically says that if there was a surface and here was the field, the vector of the surface, so suppose there's any arbitrary surface in space, then it's integrated around ds. So this is the amount of u actually the fluid, this would be the velocity on the surface dot product with the surface integral. So it basically is the amount of fluid, it relates to the amount of fluid basically exiting that surface. So if this has to equal 0, because there's no fluid, net fluid being generated in the surface, only net fluid leaving, then by Gauss's law, this also has to equal the volume integral of the gradient of u over the volume for any arbitrary surface. So this basically implies that this is always 0. That implies that this is always 0. Volume is always positive, so it basically implies that the gradient of u has to be 0 everywhere because these surfaces are arbitrary. And nowhere is there any surface where it can actually generate fluid or have fluid basically dissipate into non-existence. So that basically does that. So with the next thing to do is to basically apply these simplifications to this equation. So basically rho is going to come completely out of this equation because it no longer depends on anything, it's just a constant, so it can come out completely. And the other thing that's going to happen is this entire term is going to go away because that term contains this divergence of u, and there is no divergence of u. So what basically, next step is basically to rewrite this thing. So this is the integral t rho ux d by dt is going to equal, much simplified right hand side, in the integral over this blob volume rho is basically going to come out and have the ux still in here. This entire term disappears. Rho comes out. So this becomes just the gradient of ux dot product with the u vector for the velocity. Since I have more room, I'm going to actually write that out. It's dependence on space and time. And then it's just integrated over the volume. So there's a common, of course, the U actually has 3 components. So there's another way to write this that actually takes this into account. And it uses this type of notation. And this is pretty much just done by definition. So it basically defines U dot gradient to of a given component would basically just by definition equal the following. D by partial derivative of y, and then plus the z component partial derivative with z times the whatever component that was. So what can basically happen is this thing, gradient of ux, I'm not going to write the full time dependence right now, the gradient of ux u vector basically is defined as u vector dot and this can be expanded, so a shorthand way of writing this, which will come up later, so I'll write it down always once. It's basically to write it out like this. To basically show this equation for all the components. This is basically the same equation, except it's basically implying that this equation holds true for each component, so for ux, uy, or uz, this same equation holds. So this can be written as, which is the vector again, and I'm going to drop the explicit space and time dependence for the moment on most of this. So the partial derivative, in this case the u vector, actually I don't want the gradient yet, second though, and that's basically here is u vector, the gradient symbol, and u vector. But this is the same as this equation, except it's just showing the dependence also on y and z. However, each component equation looks like this. So, and to finish this up, this guy was originally equal to the force, as well as this is the mass side, and then there's a force term that looks like this. So this whole thing equals, so that's basically the mass times velocity differentiated by t. So this is the d by dt, mass times velocity side, which goes into that. And then we have the force side. And the force side looks like the force net times the volume. So this basically is the left-hand side of the Euler equation. The next step is to basically go into the right-hand side of the Euler equation.